All right, let's get started again. Okay, so yeah, I hope you're recharged your batteries and high energy now for the last session of today, which I'm particularly looking forward to, because I think that maybe shows us a little bit like the future of metabolomics analysis, and also like leverages a little bit like what we try to communicate here, and that is like open science and data sharing. So yeah, like in the next hour or so, Ming is going to walk us through repository scale analysis, where we actually make use of like existing data and either like contextualize our own data or look for like new patterns and new things like right into like the repository. Yeah, okay. Ming, well, welcome. Ming, hopefully you can all see him up here. And yeah, very much looking forward to your talk.
Yeah, how's everyone doing? Danny, can you swap the camera around so you actually can see people?
Sure.
Actually, hold on. You gotta turn on your actual video. Okay. Well, you can see me, but hello everyone. Okay, so yeah, so this will be a pretty quick thing to cap off the day. So thank you all for staying for the thing. I know it's been probably a long and fun, but kind of tiring week. So this is one of the things that I'm particularly excited about, especially working with we've been working with Danny. We've been developing this stuff for the last couple of years. And maybe this has been a long time coming for the field. Finally, we actually have people are depositing data, so we can do something with it. So we'll just get started. If you I think Danny uploaded the slides to the shared drive. So part of this is going to be hands-on with a few links. So it'll be handy if you have the slides ready just for reference, as well as a few links in there. So in the meantime, you can kind of get that downloaded. So giving you an overview of this next hour, we're going to learn how to leverage public data to get context for any analytes that you detect. So you'll be able to learn what types of samples and where else has been found, and maybe develop search for some analogs at the repository scales. We'll do a hands-on with domoic acid. I think you guys looked at this probably a little bit in your previous hands-on analyses over the past couple of days. And then we'll also introduce some new ways to start mining for mass spectrometry patterns, not just full molecules at the end of this. And so we'll get started with mass and just a general idea if you all haven't heard about it. And so, and feel free, I think I can see if anybody has any questions, but kind of wave your hands wildly, and then at least Danny will be able to see. So, but anyway, so kind of where this comes from, this idea that we came about with this tool called MAST, is within sequencing, number one, people actually deposit their data historically over the last 20, 30 years. And one of the tools that's become really, really kind of a cornerstone of the sequencing field is a tool called BLAST. And with BLAST, you can take any sequence that you have in your own hands and ask the question, where else have I seen this particular sequence before? What data sets, what kinds of organisms, and you can look for similar sequences to figure out function, as well as context in general. And so this is this is pretty standard. People take this for granted. And within mass spectrometry, we really haven't had kind of the similar kind of functionality as readily available, or even just we assume that this is possible until a couple years ago. And so the idea is, if you can do this with DNA sequences to blast all of short read archive or EBI or the NCBI taxonomies, shouldn't we be able to do the same thing if we have a tandem mass spectrometry, mass spectrum, and we have all this public data? We should be able to ask the same questions, like which data sets have we seen this particular molecule in, and be able to do that relatively quickly. And so at the moment, there's a couple thousand data sets reaching into the billions, or at least crossing the billion MSMS spectra. So it's not particularly small. It pales in comparison to the size of genomics, but it's definitely beyond the scope of something that you could look through manually. So, and that's what this MAST tool will allow you to do. You have an MSMS spectrum. You might know what the structure is, or you might not, but you want to be able to quickly ask, hey, where else have I seen this? So does that make sense so far? Okay, I can see a few heads nodding. But okay, cool. So that's most basic idea around it. And if you do start searching all this public data, what are the deliverables, right? Like, what do you get out of this? And so on this left-hand side, these bullet points, is you'll be able to understand what types of samples this particular analyte is found in. So we're talking about organism, disease state, the location which sample is collected, and who actually deposited or collected this data. And so there's a few more categories for the metadata that you can actually get out. But this is kind of very high level what you can kind of expect to get out of this. And there's different ways that you can annotate this public data as it's going in. And so that'll tell you, if you want to know the prevalence of this, if you're coming from a natural products perspective, you're like, oh, the organism probably matters quite a bit. You want to understand a particular bacteria that's producing an unknown molecule in higher abundance. You want to go isolate that one and actually purify it. If you care about it from an ecology perspective, you want to understand how prevalent this is being produced across many different ecosystems. And if you're coming from a traditional metabolomics perspective, maybe it's a pollutant, a xenobiotic. You want to see how prevalent this is across a population and questions like that. And if you're kind of coming from a more mass spectrometry kind of chemistry perspective, maybe you can use mass to look for the local chemical neighborhood of a particular analyte or molecule you care about. So you can fish for using a molecule that you know or you care about. You can go to all this public data and start fishing for analogs across all public data sets. So these are kind of the two areas that people have started using MAST. At least that's what we've seen so far. But that's not to say it's a pretty general tool. And so people have been pretty creative with BLAST, and we look forward to how people will use MAST. So anyway, those are kind of deliverables that are most obvious if you use the actual tool. And so now we'll go into the hands-on section. And so we have domoic acid that Danny had annotated within one of your samples. And so you all have analyzed with feature-based molecular networking in GMPS over the past couple days. And so what I've linked down here is a catch-up link to a result view within feature-based molecular networking. And directly from there, you can start searching with MAST all the public data. As a side note, working with Robin, he already integrated all these things in MZMine. So if there's a particular analyte that you find interesting in MZMine, I think there's one button you can click that says, well, MAST this particular molecule, and it's all integrated there as well. So that's just kind of a side point. But if you go ahead and click this catch-up link, it will get you to, let me pull this up, it'll get you to a results table that's been pre-filtered to domoic acid right here. Let me zoom in so we can see it a little better. Domoic acid here. And so there's actually 2 rows. But what you can start clicking on is there's a link on this left-hand side that says MAST spectrum. And if you click on that, it'll take you to, especially if you're logged into GMPS. Oh, I gotta log into GMPS. Okay, hold on.
Hey, one question.
Yes.
Maybe what would be quite helpful for the audience would be if you could show how to navigate there from like the status page of the molecule.
Oh yeah, that's a great point, Danny. So
unfortunately, I think most of the people here got their feature-based molecular network running from like the different test data sets we gave them, and I think most of them should have domoic acid in there.
Okay, that's perfect. So the view that you'll want to look on is called View All Spectra with IDs. So it should be here in the first section, the default views. And so if you click on that, it'll get you a pretty giant table. Danny likes to get a lot of features found. And so now we'll end up with like here 2,600 features. And so if we scroll to the right-hand side, you'll want to filter to domoic acid. And so that should filter you down to 2. Is everybody able to follow along, at least on their own job to that point?
In case people, there may be some data sets where you did not find it, then you can also, for the example case, just pick any molecules that you might find interesting. But I hope that most of them should contain domoic acid.
Yeah, not if you did with different data. If you didn't do with ocean data, I kind of hope you don't have domoic acid in there. But yeah, if you have the catch-up links, you can go and follow along there. And once you get to that point, and again, you can do this with any molecule that you find interesting, whether identified or unidentified. And if you click this button called Mass Spectrum, it'll automatically bring you to a search, another workflow in GMPS with the precursor M over Z and the peaks pre-populated. And so this is pretty straightforward. If you wanted to search your own spectrum that you had, it's not in the GMPS ecosystem, right? You might have collected it directly off your mass spectrometer. You can just enter the peaks and the precursor here and search that as well. So it doesn't have, you don't have to upload any data. You just have to put in the peaks here. And so everything here down here is by default. One of the things you can start doing is tightening up the mass tolerances for the parent mass and the fragment masses, and setting the match criteria. But for default, we'll just leave it as is. One area that you might want to change is you might want to search for analogs if you want to look for analog molecules of whatever you're searching against. So that's something you might want to change in the future, but we don't have to do that in today's example. So once you're done setting those particular settings, go ahead and click. Oh, I need a title. Okay, you need to put a title. So test task for domoic acid. So once we put some test task here, then we hit submit, and it'll get going. Is everybody able to follow us? Yes, and Danny's, there's a question. Why is the parent mass by default 2 Daltons, and by default everything is for low resolution? I think that's Kai. So, and let's go back. So there's some slides in the PowerPoint to guide you through all this. So this will take about 15 minutes to run. We actually have a much faster version that's still in beta, so we didn't want to demo it here. But in lieu of waiting for 15 minutes for this all to finish, we have in the slides here a catch-up link specifically for domoic acid. So if you're in the slides and you go ahead and click on this link at the bottom here, what you'll end up with is a mass job that's already finished. And if you all can go ahead and go there, we can continue on that front. Any questions so far? Okay, well, let's get going on this mass job, this demonstration. So the very first link at the very top, it's just kind of a courtesy, or it's kind of a nice to have, not super important. But if it's a single spectrum, it also does library search as a part of this, as opposed to searching all public mass spectrometry data. So it'll tell you, what it actually, what are the library matches, so you can kind of just check that it's actually domoic acid. So that's, an aside. But the more important thing is under this community matches header, there's a data set matches link. So if you click on this, what this view will tell you is, hey, this particular MSMS spectrum matches to 40 different data sets. And it gives you the title of all the data sets. So this gives you a very high level understanding of where this particular molecule is actually found in. And so this is not particularly surprising given domoic acid is, well, Danny, correct me on the biological context, but it's found in oceans. It's produced by some bacteria or some microorganism. And so as we look down the list, we can see these dissolved organic matter, ocean non-target analyses. And so it seems to be consistently being observed, number one in Danny's data sets, but predominantly in a lot of these pseudonychia marine data sets. So even from predominantly from GMPS, but we're also seeing it from data sets, I guess, from metabolites as well. So not particularly exciting or unexpected, but this is kind of kind of a positive control for us. And to just compare the fragmentation from these data sets to our own spectra, you can click on these view mirror matches to look at what is in the database and what is in our spectra, to just kind of be able to confirm the matches. Does that make sense so far? Any questions? Any questions? Feel free to chime in. Feel free to chime in.
So maybe just one comment in case people had difficulties finding this catch-up link. So it's in the PDF document of the slides of today, but I also just pasted the link in our resources document just at the bottom. So if you had not opened it yet, then feel free to open this. And maybe to add like a little bit of biological context to domoic acid. So this is a neurotoxin that is like responsible for like harmful algae plumes from Pseudonychia and quite of like some environmental health concerns. And to contextualize a little bit with like the mask results here, when I first saw that and I was like going through, what was actually pretty interesting to me was that this also popped up in data sets from like regions that are not very known for like harmful algae plumes from Pseudonychia. So I don't know, 40 hits, right? So you could go to the next page as well, Ming, and we could look, and there might be like some places where, it's not necessarily like expected. I don't know if there was some seafood in there. I don't know, but
yeah, maybe it's found in some like we ran like 3,000 different foods. So yeah, maybe it was seafood, and it kind of, I mean, the fragmentation looks pretty good, right? So all the major peaks are matching. So
particular like some of the coral reef data sets, that was definitely something I was not expecting Pseudonychia plumes to be. So here, I think it's really interesting how it contextualizes and gives you like a new view on like compounds present.
Yeah. So, and just again to recap, like what we're searching, this is a little over, I think, 2,000 data sets comprising under the hood, it will be around 200,000 LCMS runs. I think it's about 1.2 billion MSMS spectra kind of contained in all of this data. So it's a decent amount. It's a decent amount, probably a little more than you can collect in your own lab, at least within a reasonable amount of time. But it's, from contributors from all over. And so if you want this kind of capability to search your own data, like your historical data, make it public. It kind of automatically gets thrown into this. So I just think it's very cool. If you have like the last 5 years worth of untargeted data, and you want to ask the question, have I, within my own lab, have I ever seen this analyte before? You can start answering that question pretty easily. So. But cool. Any questions? Okay, so we'll move on to this very last section. It's a new project. We just put out the preprint, so you know, maybe we're very we're fickle in our interests. Anything older than like 3 years, we're like, that's old news. Let's invent something new. So and so here with MAST, we proposed, or it's a tool that allows you to search for full MS/MS spectra, like the entire molecule fragmentation against all public data. That's cool. That's useful. It can let you answer certain questions. However, one of the things that, you know, that working with Danny and working with people in the community that they kind of asked me is, can we find, since we have all this public data, can we find not a specific molecule, but certain types of compounds that they want to search in public data? So for example, like Danny might come to me with like all brominated compounds, all carnitines, all siderophores, all saccharides, and questions like this. And you know, the nice thing about some of these classes of compounds is that the fragmentation is sort of known, right? The mechanisms of fragmentation are known in tandem mass spectrometry. And so all that knowledge, number one, it can be in literature as well as just being in your heads. Right? And analytical chemists, mass spectrometrists, you have that kind of model of what'll happen when you put into a mass spectrometer in your head. But for every kind of class or subclass, I was not going to code a separate piece of software for everybody. Number one, because I'm lazy. And so, you know, kind of the thought process is, can we come up with a universal computational solution to answer these kinds of questions that, so I don't have to do any work and the chemists get to do a little bit of work. So the answer is broadly, we think yes, that we can create a solution where chemists can start finding exactly what they're looking for in mass spectrometry data with as much specificity as they want. And so the solution that we came up with is called the mass spectrometry query language, and MassQL for short, and we have a little logo in the top right corner. And so the kind of the goal here, or the set of goals, is that number one, it needs to be understandable. So it needs to be easy to read and write for chemists. So you can express exactly what you're looking for in more or less kind of a natural-ish language. And it needs to be flexible. So you need to be able to say exactly the kinds of patterns that you want to express within mass spectrometry across MS1, MS2, MS3, whatever kind of mass spectrometry you have, as well as mass spectrometry adjacent features. So like retention time, mobility, and kind of in the future, if you have UV, vis, and these kinds of other measurement modalities that come with the mass spectrometry data. It needs to be scalable. And so these are probably patterns that you're looking for manually today, right? So if you're looking for carnitines or specific fragmentation patterns, you're probably looking at whether you or your grad student or your postdoc, you're looking at maybe spectra one by one within a sample, and that's fine. I'm particularly lazy, so I can't stand any manual work, but you know, that's good if you have like one sample, but this becomes less fun if you have even a dozen samples, and becomes just impossible if you have 100,000 samples at the repository scale. So we want, if you express a particular pattern, you can search one file, or you can go all the way up to the entire repository. And we want this to be reusable, right? So if you encode your knowledge essentially as a little sentence, you want to be able to not think about that again, right? You can give this to your a trainee so that you don't have to, you can get them started to analyze data, and you can share it with people across the community. And so those are kind of the four pillars of MassQL. And just to give you an idea, so again, this is brand new, working with Danny, some of the things that he's looking for are some natural products. And this is one thing that he worked on during his PhD. And so this is a family of aldecidin molecules And these are NRPS, PKS, natural products. And he knew that there's particular fragmentation patterns that are conserved within albucidins. It just visualized here from structure to fragment. For example, this 468 and 660 M over Z fragments are quite large in all these families of albucidins. And he's able to express that in a little query here in the bottom left, saying, hey, find me all the MS2 data where there's a 468 and a 660 fragment. And so this is pretty bare in terms of qualifying the peaks, but this just shows the principle. And so he was able to express that and find all the albucidins that he had published on. So that's kind of the positive control, as well as find new ones in the data that he'd already published on that he didn't know that were there at the time. So that's kind of cool. And just to give you an idea of the flexibility, it's actually a little bit, it's more flexible than this, but it's just a little hard to explain in a short amount of time. But the most core things that we can explain or that you can represent are in the top left peak masses. So there's a particular fragmentation or MS1 peak that's interesting. Peak losses from precursor in the top right, as well as gaps between peaks. So if there's any two peaks that differ by some amount that you want in your MS1 or MS2 spectrum, as well as the relative peak intensities. So that might indicate something about what is the composition of the molecule you're looking for. And this can be across MS1 and MS2 data currently. And so you can have some pattern, like an isotopic pattern, for example, that's unique across MS1 and even across adducts. And then you also coincide a pattern in the MS2. So it allows you to have whatever little bit of information you know about what you're looking for, it allows you to inject it at exactly the right place. I don't know if Allegra showed you, but she's doing some cool stuff looking for siderophores, and there's like some fancy queries there that we're working out and looking at repository scales, and so that's kind of getting into the medium advanced applications. But any questions so far? Cool. So I think there's a question in the chat. Allegra, you answered it.
Yeah.
Okay. I think there was also a question from the audience. Sorry, I just.
Okay.
So you have to make your own. You have to find your own unique pattern first for a feature, then you can run it. And your way of searching for that class will that be saved so others can use it. You get like a score for it. So it gets rated like you get very good results in this data set for your thing that you're looking for. Like that?
Did you fully understand that, Ming?
I couldn't hear anything. Can you repeat it, Danny?
Oh yeah, okay. So I think the main question is, are like those searches like somehow stored, and can others use those queries? Is that correct?
Yeah, that's a great question. That's a great question. So first, especially if you write the query, like it might take, first of all, you can dump your knowledge that you accumulated over like 10 years. It might take you 30 seconds. So you want to share that with others. So first, these queries are just going to be text sentences, right? So it's going to be pretty succinct. So number one, you can just email them to somebody else, or and then they can just copy and paste and apply it to their data. So that's number one. But to memorialize it even further, there's a tool called the MassQL compendium, where you can contribute. It's kind of like a spectral library of sorts, right? So you can contribute your query and you describe in detail, saying it's looking for this. Here's the mechanism, and then that will be reusable by. I'll show it in a quick second, and that'll be reusable by others, and people can find it. And so and also working with Allegra, Danny, and our other friend, Alan Jarmusch, we want to have a special issue of, in some journal where people can contribute their own MassQL queries, but more fully describe the mass spectrometry mechanism and apply it to real data. So it's kind of a it would be a collection of technical notes. And then you can fully describe and convince others that, hey, this is really cool. Or like your particular pattern is correct, usable, and ultimately encourage others to reuse it. So does that answer the question?
Yeah.
Okay, awesome. So we'll go into the example phase now. And so this is a super simple example. And so one class of compounds that we might be interested in are molecules that contain glycans. This is not the most fancy thing in the world, but one of the things that just a small molecule here, one of the things that you might observe when a small molecule contains a glycan is a neutral loss from the precursor. So the glycan falls off first. And so just as an example here, we wrote out the query. So just to describe this, I actually have the full description here because we translate these things over to a lot of languages. So if you write a query, it translates it to like English, Portuguese, Spanish, German, Chinese, Korean, Russian, French, and German, I believe, is the full set of languages. So if you write your own query, so you don't have to explain it to anybody else. But if you write a query here, it'll say, return to me all the MS2 data where there's an MS2 neutral loss peak of 162 point something, and it must be at least 10% intense and within a ppm tolerance of 5. So this is kind of the very basic pattern that we're going to be looking for to look for glycan containing compounds. And so we're going to try and apply this to real data. And then the way we're going to apply this to real data, there's an interactive sandbox link here that'll have the query pre-populated. And this sandbox will, number one, for whatever queries you have, will allow you to visualize the query and show the translations, so it can help you explain what's going on. And number two, you can actually try it against GMPS public spectral libraries. So these are annotated MSMS spectral libraries. This is allowing you to have like positive and negative control data, as opposed to applying it to unknown raw mass spectrometry data, which you can do as well in a workflow, but this allows you to kind of play with it with some known data that you're querying against. So if you're able to go to this link, what you can see is the query is pre-populated here in this top left box here. And you'll have this visualization panel. So you can kind of see this. This is not particularly interesting, but it'll visualize the query for the MS2 portion here. But for now, what we're going to do is click the Show Hide button and hide the query visualization. And there's another panel here called Data Exploration. So this is the actual results if whenever we apply this query against this particular file called GMPS-library. So this is a subset of the GMPS spectral libraries. And we're going to visualize the results from there. So we'll give you a few seconds to kind of click on this and show hide, and I'll walk you through what the results will show. Are we back, Danny?
Yeah.
I think I got dropped for a second.
Yeah, you're back. Good to go.
Okay. Okay. Is everybody able to go to the sandbox? And everybody, it looks kind of like my screen. Okay, cool. So speak now, or at least hold your peace for another 5 minutes. So what you'll see here is, because we have this query here and we're searching against the spectral libraries, if you scroll a little bit to the right, what you'll see is this table. And this table tells you all the results that were pulled out. So all the MSMS spectra that had this particular pattern we're looking for in the spectral libraries. And so it's about 8 pages, so about 70-ish compounds. But we can see the names of the compounds where we can find them. And so we can notice, you can Google, if some of you might recognize these names, but some of these other compounds you can kind of see in the names themselves, they have like hexacide as part of the name. And so this gives us some confidence that what we're finding in the MSMS that we're finding do contain a sugar as part of the molecules. And if you Google some of these other compound names, look at the structures, they're actually natural products that have a glycan on it. So you can kind of keep scrolling across the subsequent pages. And most of these actually do have a sugar on them. So this, just going back to the slides, this gives us some confidence that what we're finding actually, is what we meant to find, right? So this pattern is reasonably selective for glycan-containing molecules, at least in the spectral libraries. And so, we can do more detailed benchmarking for specificity and sensitivity, but this allows you to, kind of qualitatively assess that against the libraries. And so if you're confident in what you're finding here against the libraries, you can take these queries and deploy this on your own data to find, to subset your data to what you actually want to look for, certain classes of compounds that you're looking for. And we've done this across, entire repositories. And so you can go from 1 billion spectra down to a couple 100,000, but that's still quite a bit. And so we've coupled these tools together with molecular networking. And so one of the things that you can do, for example, with the carnitines or glycans, is you can go from 1 billion compounds in all public data, look for all glycans or carnitines, get that subset, and then visualize that diversity in a molecular network. So now you have not just one family of a molecular network that maybe contains glycans, but your entire molecular network will have all glycan-containing compounds, and each family will be a very specific class or subclass within that. And so that's one way, if you are particularly interested in a certain type of compound, you can start exploring the repository scale, a data-driven way of looking at the diversity of that molecule across everybody's data. And so we've done this for looking at some flame retardants, so organophosphate esters, and we've discovered some new flame retardant of that particular class that hadn't been characterized in literature before. With Allegro, we're looking for siderophores against public data, and so we're putatively finding some new ones. We're also looking for all bile acids that we can find and looking for new family members, and we're seeing quite a few of these. So those are just a few, as well as working with Raphael Reher he's at the University of Marburg. He's a natural product guy, and he's looking for all these polybrominated compounds, finding some new analogs of these eagle toxin things. So there's a lot of space here, as well as working with Alan Jarmusch at the NIH. He's looking for all glucuronidated molecules that indicate, xenobiotic metabolism. Things, so spans the gamut from more traditional metabolomics to natural products to environmental chemistry and things like that. And so if you wanted to actually use MassQL today, we're trying to create a rich software ecosystem. So there's a Python API, there's an R API, and there's the sandbox, and then these workflows at GMPS that you can use to really get you kickstarted. And these are all free, kind of open source for academics and industry, as well as working with people like Robin, Hiroshi, Axel, and Michael Marty. It's being supported in these newer versions of like MZMine, OpenMS, MS-Dial, Unideck, in GMPS workflows and the GMPS dashboard. So it's kind of being more pervasive. So if you do write a query once, you'll be able to repeat that analysis on any, kind of the goal is any data on any platform for any sort of pattern that you want to look for. So, kind of this universality concept. And, this wouldn't have been possible without, a ton of co-authors and collaborators. So definitely, Allegra, Danny, Alan, and a lot more people. But if you want to try out MassQL or MASS or any of these other tools for repository scale analysis, definitely reach out. And happy to help facilitate those things. Any questions so far? Cool. And we've got one final thing for you all.
Do you want to check in the chat? Was there something?
Oh yeah, I think Allegra answered it. Okay, so the question is how are catalog the MS2 data? Oh, okay. Right. So the question revolves around, when people deposit MSMS spectra, do they need to tell us that this is an MS2 peak or this is an MS2 neutral loss? So broadly, no. It operates purely on, what we assume to be mass spectrometry data, right? And we can compute out what the neutral losses are, what the fragment masses are, and intensities. You don't people don't have to do anything different. And so when you apply MassQL on GMPS libraries or raw mass spectrometry data, we read the formats natively. And we understand from the mass spectrometry data type, how do we translate that into this query space? So bottom line, you don't have to think, it just needs to be in open formats. If you want to query, or if you deposit them in spectral libraries like a MassBank or GMPS or anywhere, it'll just understand it. At the end of the day, it should be easy. At least that's the hope. So yeah, if you have questions after this, happy to answer them offline.
Hi, Ming. This is Mabel. The other question that I wanted to ask you is, have you think about doing a mass for GCMS data?
Yeah, GCMS is a little bit more tricky. I think it's feasible. I think on the GCMS side, at least Oliver Fien's group has their bin base, which is kind of similar in spirit with regards to using GC, and you can kind of search for a particular analyte, but it's all the data is sourced from a single place, right? So the deconvolution requirement for GC data, it makes it a little trickier. And so for bin base, it works because it's all from the Fien lab. So I think it's doable. Oh, there's one other resource that I think that actually tries to do this already now. So this is from Shuja Du's group at North Carolina. So there's ADAP Cloud. And so they've been processing a lot of GC data and doing the deconvolution and making that data available for search. And so I think that's a reasonable place to try out. And we've been talking to them about integrating some of our tools to make the searches really, really fast. But I think I'm not an expert GC, so if it were going to be possible, it will be in collaboration with somebody like that.